Hello there, Mr. Sutton here with the BC Calculus 8-4 Extra Practice number 7 solutions on vector free response practice. For this no calculator based free response problem, we have a particle moving on this circle here, so its position vector at any time is given by this set of coordinates. First task is to find the velocity vector. So to start that, basically we need to take the derivative of position, which means taking the derivative of x of t and y of t independently. For both of these, we're going to have to use the quotient rule. So let me set up my box and ribbon here for the derivative of the x term here. That's going to be a numerator of 1 minus t squared, denominator of 1 plus t squared, and the derivatives of those will be negative 2t and positive 2t. Multiplying that out, we've got negative 2t times 1 plus t squared, so going this way. And then going the other way, we have minus 2t times all that stuff, all over 1 plus t squared squared, so that's the v squared down there. And even though I don't need to simplify this, I'm going to, because I know I'm going to need a more simplified version of my velocity vector for the problems that are coming up here. So let me get this out of the way. This will be negative 2t minus 2t cubed. And then let's see here. For this one, we've got minus 2t, and minus, that's going to give us a positive 2t cubed over there. Combining like terms, we have negative 4t, and then the t cubes are going to be canceled out. So there's my x prime that I can now use. For y prime, we're going to have to use another box and ribbon, another quotient rule. So for y prime, let's see, for y we have 2t for the numerator, and 1 plus t squared for the denominator. Derivatives of those are 2 and 2t. Multiplying that out with my quotient rule, u prime v minus uv prime over v squared. Here's y prime. We've got, going with the ribbon here, we've got 2 times 1 plus t squared minus 2t times 2t, all over 1 plus t squared squared. And simplifying that, we've got 2 plus 2t squared, and let's see, denominator's unchanged. We've got a minus 4t squared there, so that's going to be a grand total of 2 minus 2t squared. And then because I haven't actually written the velocity vector out, I'm just going to write x prime of t comma y prime of t, and we've already told them what x prime of t and y prime of t look like algebraically, so we're good to go. For this part, they want to know if the particle is ever at rest. Well, the particle will be at rest if x prime and y prime are both 0 at the same time. So let me take, well, first off, here's my x prime and my y prime that I found in part A. Let me take my x prime and set this equal to 0 and solve. And then any t values I get that make x prime 0, I'll test them out in y prime and see if we also get 0 there. So setting x prime equal to 0, the only place that this is going to get zeroed out is if the numerator is 0. So negative 4t equals 0 is the way to go on this. And if we do that, we see that t equals 0 is the only place where x prime is going to be 0. Does a t value of 0 make y prime 0 as well? So let's do y prime of 0, plugging 0 in for all the t's in there. And let's see here. This is going to be 2 minus 0 on top. So we have a 2 in the numerator. Down below, we have, this is just going to come out to 1. So this is a grand total of 2, which is not 0. Because the only place that makes x prime 0 does not also make y prime 0, that means that we're not going to be at rest anywhere at any time. For the last part of this problem, we want the coordinates of the point that the particle approaches as t increases without bound. So basically, as t approaches infinity, what point are we trending closer to with this position function? So I'm going to do this individually for x and y. I'm going to take the limit as t approaches infinity of x of t, which is the limit of this expression here, this first position coordinate. So as t approaches infinity, we basically choose our champion on each side, ignoring the slower growing terms. So the numerator, we can think of that as just being negative t squared, and the denominator, we just look at t squared. And then if I divide those easily cancel out to give me just negative 1. So negative 1 is the x value we're heading towards. How about the y value? So limit as t approaches infinity of y of t, That's this 2t over 1 plus t squared expression that we're taking the limit of. There we go. Had an extra equals in there. So limit of this thing, this is a bottom-heavy function. T squared is a faster growing function than t. Therefore, this is going to go to 0 as t approaches infinity. So overall then, our point that we're going towards is going to be -1, 0. For this free response problem, which we're allowed to use a calculator on, we have a particle moving in a plane so that its position between times 0 and 2 pi is given by this parametric set of equations here. Our first task is to find the slope of the path of the particle at time pi over 2. So for this, we need dy over dx. Before we can even find that, though, we need to know the derivatives of x and y with just respect to time. So I'm going to start by finding equations for x prime of t and y prime of t. Now, on this particular problem, and even part B, I don't actually need to know what the derivatives look like algebraically to do those problems and show enough work. But I am going to need x prime and y prime written out, the general versions of those, for part C. So I'm going to find those now, and then we'll just have them to use. So for both of these, we're going to need product rules. So we need the form u prime v plus uv prime. I'm going to set up the box and ribbon and take care of x prime first. So I have my u and v values of e to the t and sine of t. And the derivatives of those are also e to the t, and this one's going to be cosine of t. So x prime then we can write as, just using the ribbon here, e to the t times sine of t plus e to the t cosine of t. So now I can use this x prime to stand for all this stuff, and people know what I'm talking about. Great. Now we need to find y prime of t. That's another product rule, so here's another box and ribbon. This time we've got e to the t and cosine of t, so this one's going to look kind of similar to this one. We have e to the t again for that derivative, and now this is the big difference. Cosine's derivative is negative sine of t. Multiplying that out to get y prime, I've got e to the t cosine of t minus e to the t sine of t. So now to get dy over dx, which is the slope of the path of the particle, I need to do basically y prime of t over x prime of t. And if I want this at time pi over 2, I need y prime of pi over 2 over x prime of pi over 2. I'm going to do this whole thing on the calculator. Now that I actually have these defined, I can just plug it in. So here I am in my grapher in the y equals, and it was a little bit of a chore, but I took the time to enter x prime as my y1 here, and y prime I've entered as my y2. So now I have those to use whenever I need them, and I kind of need them now because I needed to do y prime of pi over 2 over x prime of pi over 2. So let me quit out of here, and I'll do, let's see, fancy fraction. So that's alpha y equals n over d. And now to do y prime, I'm going to do alpha trace y2 because that's where I stored y prime. Open a parentheses, and I'm going to put in pi over 2. And then down below here, I'm going to do x prime of pi over 2, so alpha trace y1. Open that, and then pi over 2. All right, press enter, and comes out to exactly -1. Hey, we'll take their word for it. On this part of the problem, I want the speed of the particle at time 1. So this is going to be the square root of x prime of 1 squared plus y prime of 1 squared. So this is our general setup. Now, I already defined x prime and y prime back in part A, and even if I didn't, I've got x and y defined, so I could just take these derivatives at 1 on the calculator without showing any other work. But I'll use the functions that I created and already entered in my calculator. Let's do that now. So here's what this looks like on my calculator. Recall that I stored x prime as y1 and y prime as y2. So I'm basically plugging 1 into those, and to square them, I just put the square after the closed parentheses. So pressing enter, we end up with about 3.844. There was no units on this one, so we don't give them any units back. For this last part of the problem, we want the distance traveled by the particle from time 0 to 1. So for this, we're going to take the integral from 0 to 1 of basically the speed of the function. So integral from 0 to 1 of the square root of x prime of t squared plus y prime of t squared dt. So this setup. This is the part where I needed to have x prime and y prime explicitly defined in order to use them in this kind of integral. So let me go to the calculator now and use them. And this is what it all looks like on the calculator. X prime was y1. Y prime I defined as y2 and put it in there. So pressing enter for all this, we end up with a distance of 2.430. For this calculator-based free response problem, I've got the position of a particle given by this set of parametric equations. My first task is to find the speed of my particle at time 4. So to do this, I need to know a little bit about x prime and y prime. So I've got some options here. Since I've already got x and y defined, I could just take their derivatives using my calculator at time 4 without showing what x prime and y prime actually look like algebraically. But just kind of looking ahead on this problem, I notice in part B they want me to find the total distance, and I happen to know that I need explicit formulas for x prime and y prime for that purpose. So I'm going to go ahead and find those now, and then we'll just use them on this problem too. So for x prime, just using my power rule, that's just going to be 2t. I mean, it's not like it was all that hard to find it. And then for y prime, we've got, let's see, 3 times 2/3 is 2t squared. All right, I think I spent longer analyzing whether or not I needed to find these than I did actually finding them. So now for the speed of the particle, that's going to be the square root of x prime of 4 squared plus y prime of 4 squared, which I can now do on the calculator. So to start us off here, I've actually entered x prime as y1 and y prime as y2. These are not super complicated functions. I could probably do a lot of this in my head, but I'm eventually going to have to do something on the calculator if I want like a single decimal answer. So might as well start here. So let me take now the square root of, and now to do x prime of 4, I'm going to do alpha trace y1, because that's where I stored x prime. Open a parentheses, plug in 4, and then square all that, plus alpha trace y2, and pretty much the same idea. Open a parentheses, plug in 4, and square that. Press enter for the whole thing, and we get 32.985. There we go, 985. Now, just as a point of clarification here, I prefer to round up when we have a number higher than 5 or higher on the next decimal. But by AP standards, I could have written 984, and just truncating it actually would have been considered acceptable as well. For this part, they want the total distance traveled by the particle from time 0 to 4. So for that, I'm going to need the integral from 0 to 4 of essentially the speed, so square root of x prime of t squared plus y prime of t squared dt. Now, the good thing is that I've actually already explicitly defined x prime and y prime back in part A, so I can just write those here and use this and plug it all in the calculator, and people will know what I'm talking about. Here's my setup for this on the calculator. I have my integral from 0 to 4. X prime I stored as y1, y prime was y2, so I just square those without opening any kind of parentheses. And I'm using x instead of t, but because I'm using x everywhere, it functions in my integral just like the t over here is functioning in this integral. So pressing enter, total distance is 46.062. On this one, they want us to find dy over dx as a function of x. So to start this, since we already have x prime and y prime, we can write dy over dx as y prime of t over x prime of t. And just to explicitly write that out, which I'm going to need to do the rest of this problem here, remember y prime of t was 2t squared, and x prime of t, which we found in part A, but I can find it again here, was just 2t. So we can reduce that then, just cancel the 2's and some t's to just give us t. All right, so how do we turn this into a function of x? Well, we have a function, we have an equation that has an x in it, this one right here, where we could have written x equals t squared minus 3. Since my dy over dx has only t's in it, I'm going to try to isolate the t variable in this expression to be written in terms of x. So let's see here. If I add 3 to both sides and take the square root, I've got square root of x plus 3. And since time has to be positive, we don't have to worry about writing plus or minus right here. It's just going to be the positive root. We don't want to get negative time. So this is what t equals. Now, what does dy over dx equal? Well, dy over dx actually equals t. I mean, it could have equaled something else with a t in it, and then we would substitute this for t either way. But because dy over dx just equals t, that means it also equals radical x plus 3. So that ends up being our derivative in terms of x.